Section 2.8 is going to be function operations and compositions. So what we have here is a revenue and a cost function. Revenue is 168x and cost is 118x plus 800, and it's showing DVDs and dollars. So the revenue and cost obviously intersect here at the equilibrium point. But if we wanted to make a new function that was about profit, then if you remember that profit is revenue minus cost, so we could make an entirely new function by taking the revenue function, r of x, and subtracting the cost function, c of x. They've done that here with numbers, so they've figured out for 30 DVDs, well, 30,000 DVDs, if the revenue from 30,000 DVDs is 5,040 and the cost is 4,340, then you subtract those to get the revenue for 30,000 DVDs by subtracting those. But you can also do that just with the functions themselves. So I could take, to get an entirely new revenue function, I could take P of x, whoopsie, that's supposed to be a P. P of x would be r of x minus c of x, r of x being 168x, and c of x being 118x plus 800. Now, I didn't put my r of x in parentheses because there's no reason for it to be in parentheses. It could be, but it doesn't need to be because there's not subtraction out in front of it. There's no exponent. There's no multiplication. It's just plain. So I can keep that the way it is. But I need parentheses around my second one because I'm going to need to distribute that subtraction to both of those terms so that I have 168x minus 118x minus 800. So that is going to give us 50x minus 800, which would be our entirely new revenue function that we could substitute in any value for x and get that figured out. So here are the basic function operations that we can do with functions. Oddly enough, we can add them together. So if you see f plus g in parentheses with an x, that just means to take your function f of x and add your function g of x. If you see f minus g of x, take f of x and then subtract g of x. I'm going to ask you though to put this g of x here inside a set of parentheses so that we remember always to distribute that negative like we did in our little example up there. F times g of x, we're just going to take f of x and multiply by g of x, and again we're going to want both of those actually inside sets of parentheses so we remember to box distribute or FOIL or whatever we have to do there. Then f over g of x, you take f of x and divide by g of x. There is a restriction that g of x is not allowed to equal 0 because we can't divide by 0. So these are the operations we can do with functions, and that's what we're going to practice in this section. The domain for these combined functions is going to be the intersection or overlap of the domains of the original functions. And we will practice that. So let's go ahead and highlight. The domain of the combined functions is the intersection of the domains of the original functions, but we also have to consider the domain restriction if we have something in the denominator. Oh, you need to start your test. Okay. I have to pause for a second, guys. I gotta get something for someone real quick. I'm so sorry. Yeah, okay. All right, let's do some operations on functions. Oh, looks like I'm front and back. If there is a number instead of an x, then what we're going to do is just substitute into the original functions and do the operations that are shown. So that's what we have going on here. These are actually easier if there's a number than if there's an x. So we'll practice the more straightforward kind first. So we have f of x, which is x squared plus 1, g of x, which is 3x plus 5, and we're supposed to find each of the following. So when we see f plus g of 1, that means we're going to do f of 1 plus g of 1. F of 1 means to find the function whose name is f and replace all of the x's with 1's and then work through that answer. So f of 1 is going to be 1 squared plus 1. And then I'm going to add to that g of 1. G of 1 means to find g of x and replace the x with a 1. So 3 times 1 plus 5. And then we work through both of those. So on f of 1, we've got 1 squared plus 1, which makes 1 plus 1. And then 3 times 1, 3 plus 5. Add those all together, we get 1, 2, 5, 10. So f plus g of 1 is 10. Okay, we're just going to do some more that are like that. F minus g of 3. That means to take of negative 3. F of negative 3 and subtract, remember that second one needs to go in parentheses, subtract g of negative 3. So we're going to find f of negative 3 by replacing that x with a negative 3. I need to put that negative 3 in parentheses so that I remember to square it correctly. So negative 3 squared plus 1, subtract g of negative 3. So replace that x with negative 3. 3 times negative 3 plus 5. And then just work through what you've got. Negative 3 squared is positive 9. So we have 9 plus 1. Subtract. Keep that guy in parentheses until we get it all simplified. 3 times negative 3 would be negative 9 plus 5. So this is 10. Subtract. Negative 9 plus 5 is negative 4. And remember that when we subtract a negative, that's really the same thing as adding. 10 minus negative 4 would be 14. So f minus g of negative 3 is 14. Okay. F g of 5. Now this is written differently than it was on the previous page. You don't always have a dot in between to show multiplication, but those two sitting next to each other means that we are multiplying. So f g of 5 means that we're taking f of 5 times g of 5. For f of 5, remember you're going to be replacing 5 for the x in f of x. So that will be 5 squared plus 1. And then we're going to multiply that by g of 5. Oh, did you see what I forgot to do? I forgot to put those both in parentheses, but I'm going to remember now. So f of 5 times g of 5. Get those in parentheses. 5 squared plus 1 is f of 5, and then g of 5 is 3 times 5 plus 5. Now, by the order of operations, I have to finish what's in the parentheses before I multiply. So I'm going to do 5 squared plus 1, and then 3 times 5 plus 5. Keep finishing. I got 26 times 20. Let's see, 26 times 2 is 52, and then times 10, so 520. So f times g of 5 would be 520. And then our last one, we have f over g of 0. That means we're going to do f of 0 over g of 0. F of 0 means to replace the x with 0 in f of x. So we got 0 squared plus 1 over g of 0, which means replace the x with 0 in g of x. 3 times 0 plus 5. Work through the numerator separately from the denominator. 0 squared is 0, so 0 plus 1. The denominator, 3 times 0 is 0 plus 5. So we end up with 1/5. So f over g of 0 is 1/5. Now on those ones we had actual equations, but sometimes we don't have equations. Sometimes we have other representations of our functions, like a graph or a table. This one does have equations. So we're going to practice those same skills but using different representations. We're going to do f plus g of 4 for each of the three, f minus g of negative 2 for each of them, f times g of 1, and f over g of 0. So f plus g of 4. In A, when we do f of 4 plus g of 4, f of x is blue in their picture. G of x is kind of that pinkish color. I don't know what to call that. I'm not sure I have a color that's going to match that. Maybe this one. That'll be close enough. Okay. F of 4, we're going to look on f of x, find where x is 4, and figure out that y value is right here. So this ordered pair 4, 9 tells me that f of 4 is 9. And I'm going to add to that g of 4. G of 4, I go over to 4 on x, and on g of x, that ordered pair is 4, 2, it looks like. So 9 plus 2. So f plus g of 4 would be 11. What's that look like on the table? On the table, f of 4 plus g of 4, we'll just use those same colors. Here is f of x. So f of 4 would be 9. Oh, this is the same problem. 9 plus g of 4 is 2. So we still get 11. And then we have the equation representation. So here is f of x, that's our blue graph. Here is g of x, that's our pinkish graph. So we would substitute in 4 to f of x, so we'd have 2 times 4 plus 1. And then we would substitute in 4 for g of x, so we'd have square root of 4. 2 times 4 would be 8 plus 1, and square root of 4 is 2. 8, 9, 10, 11, so we still get 11. So we should get the same answer in all three of the boxes in each column. It's just different representations. So let's move on to f minus g of 2. Remember, when you're doing f minus g, we're going to do f of negative 2 minus, put your second one in parentheses, g of negative 2. F times g of 1 would be f of 1 in parentheses times g of 1 in parentheses. And f over g of 0 would be f of 0 divided by g of 0. So let's look, the table is probably the easiest one, to be honest. So let's do the table for all of these, and then we'll go back and look at the others. F of negative 2 is negative 3. So f of negative 2 is negative 3. Subtract g of negative 2. G of negative 2 is undefined. So we cannot do this problem. If one of our values is undefined, then we're not going to be able to add it to anything or subtract it from anything or multiply it or divide it. So since g of negative 2 is undefined, we can't do any of these operations. Let's see what it looks like if we were to try and do this on the graph. G of negative 2, if you look on the graph, where x is negative 2, there is no function g of x. That's because negative 2 is not in the domain of g of x. What is the domain of g of x, by the way? If we scan that from left to right, g of x starts at 0 and goes to infinity. So the domain for g of x would be 0 to infinity. so I can't evaluate it at -2. What would happen if I tried in the equation? G of -2 would be the square root of -2. And if we remember that from chapter 2, I think it was, chapter 1, I don't know, long time ago, when we have a negative inside the radical, that's going to be a non-real answer or an imaginary value. So we can't do any of these. So this whole column is off limits. How about f of 1 times g of 1? According to the table, f of 1 is 3. And g of 1 is 1. So f of 1 times g of 1 should be 3. Looking at the graph, f of 1 takes me to the ordered pair, 1, 3 right there. So f of 1 is 3, and g of 1 takes me to the ordered pair, 1, 1. So 3 times 1, also 3. What about in the equations? F of 1 would be 2 times 1 plus 1. G of 1 would be square root of 1. 2 times 1 is 2 plus 1, and then square root of 1 is 1. So we got 3 times 1, which gives us 3. Shocker. How about f divided by g of 0? So I need f of 0 divided by g of 0. F of 0, according to the table, is 1. G of 0, according to the table, is 0. Oh, mercy. I cannot do 1 divided by 0. Because I put g of x in the denominator, I have to avoid g of x equaling 0. So if I look at my table, I can see that g of x is equal to 0 when x is 0. If I look at the equation, when is the square root of x equal to 0? Well, if I do square root of x equal to 0, square both sides, I get x equals 0. So I can't evaluate g of f over g of x when x is 0. So none of these are going to work either, because 1 divided by 0 is undefined. Now we're going to look at more examples of how to know when our operations with functions isn't going to work when we turn the page and look at using just x's to do operations of functions. Let's check that out. Okay, f of x equals 8x minus 9, g of x equals square root of 2x minus 1. So if we are going to do the operation, I'll make f of x blue still and g of x green. F plus g of x means I'm going to take f of x plus g of x. So f of x, f plus g of x means f of x plus g of x. F of x is 8x minus 9. G of x is square root of 2x minus 1. Nothing in here is a like term, so I cannot combine it. So I'm just going to have to leave my answer like that. That is the answer for f of x, f plus g of x. That's it. That's all I can do. But I want to look at the domain for f plus g of x. In order to do that, I need to figure out the overlap between the domains of f of x and g of x. So we have to go back to how to figure out domain from previous sections of chapter 2. Remember that for domain, there's only 2 restrictions that we have to be concerned about. One is if I have an even index radical. So if I have some stuff inside a radical, like a square root, like I do here, to find the domain, I'm going to take the stuff out of the radical, set it greater than or equal to 0. That's how I find the domain. If I have a fraction with anything in the numerator, I can ignore anything that's in the numerator. But if I have stuff in the denominator that has variables, I have to set the stuff in the denominator not equal to 0, and that's how I figure out what to exclude from my domain. So there's 2 things we have to watch for. Only 2. 1 is stuff inside a radical. 2 is stuff in the denominator. Those are the only 2 things we have to watch for. So in f of x, the domain is not restricted at all. So for f of x, the domain is all real numbers. So I'm going to go ahead and put that on my graph, because the domain for f of x has no restrictions. So f of x is going to be all real numbers, negative infinity to infinity. So I'm just going to color that on my graph. F of x can be any number. What about g of x? G of x. G of x does have restrictions. It has a radical. So I need to take what's inside the radical, set it greater than or equal to 0, and I need to solve that. So I'll add 1 to both sides. I get 2x is greater than or equal to 1. Divide both sides by 2. I get x is greater than or equal to 1/2. So on my number line, if I find 0 and I put a closed circle on 1/2 and shade to the right, that's the domain for g of x. It goes from 1/2 with a bracket to infinity. So the domain for adding these functions together is going to be where those 2 overlap. So the f of x is in pink, g of x is in blue. The overlap will be purple. So we can see that the overlap goes from 1/2 to infinity. So the domain for all of these problems that we're going to do, except for probably D, that domain is going to be from 1/2 to infinity. Now why is letter D going to be different? Because in letter D, I also have stuff in the denominator. So we're going to look at that one separately when we get to letter D, but for A, B, and C, the domain will be the same. It's going to be the overlap between the pink and the blue. So let's do the rest of our operations. On B, we have f minus g of x, which, remember, we want to take f of x. It doesn't need to be in parentheses, but g of x does. So f of x minus parentheses g of x. F of x was 8x minus 9, and then minus parentheses g of x. G of x was square root of 2x minus 1. There's no way for me to distribute that subtraction into that square root. So this is going to end up just being 8x minus 9 minus square root of 2x minus 1. I can't simplify anything else, so that is just my answer to f minus g of x. And the domain is the same as the first one, 1/2 to infinity. Letter C, we have f g of x. Remember that f g of x means multiply. So I'm going to take f of x in parentheses times g of x in parentheses. So that's going to give me f of x was 8x minus 9. So 8x minus 9 in parentheses times g of x, which was square root of 2x minus 1 in parentheses. Now I can go ahead and distribute this square root to both of those terms. So I can distribute square root of 2x minus 1 to both of these terms, which would end up leaving me 8x square root of 2x minus 1 minus 9 square root of 2x minus 1. Now I can't combine anything, so that's just going to be the final answer. And then the domain will be the same as it was in A and B, from 1/2 to infinity, because it's the overlap between those two sections. Letter D was f over g of x. Remember that f over g of x means to take f of x over g of x. Since f of x was 8x minus 9, and g of x was square root of 2x minus 1, hopefully they won't make you rationalize the denominator. I definitely would not. I'll show you what it looks like if you have to, because sometimes my math lab does weird stuff, but I would just leave it like this personally. I would accept this answer on a test. Let's look at the domain though. This domain has an additional restriction because we just put a variable in the denominator. So that restriction says that I have to take the denominator and set it not equal to 0. If I work through that by squaring both sides, that gives me 2x minus 1 cannot equal 0. Add 1. 2x cannot equal 1. Divide by 2. X cannot equal 1/2. So I have the domain currently that says x is greater than or equal to 1/2, but now I also say x cannot equal 1/2. So if I say x is greater than or equal to 1/2, but x cannot equal 1/2, then that's going to give me x is just greater than 1/2. So the domain for this one is going to be parenthesis 1/2 to infinity, because I can't include the 1/2. So let's look at what it would be like if we had to rationalize that denominator. It's pretty easy because there's only the one term. So all I need to do is multiply the numerator and denominator both by square root of 2x minus 1. In the numerator, that's just going to make me have 8x minus 9 times square root of 2x minus 1. In the denominator, the square root of 2x minus 1 times the square root of 2x minus 1 just makes 2x minus 1. You could distribute that radical, so it could end up being 8x square root of 2x minus 1 minus 9 square root of 2x minus 1, still all over 2x minus 1, but like I said, I wouldn't make you do this, but just in case my math lab does, that would be the steps.